everyone. This video is going to be showing you the fifth chapter in our textbook today, starting off with tiling. So I've got some shapes here that I'm going to be working with, but put shortly, tiling is a way for us to take a shape or a series of shapes and fill up that space so that all the pieces fit together and we've entirely covered 2D space like we have here. You can see, and you probably know already from experience, that these regular triangles tile the space. So just a reminder, regular polygons have all the interior angles the same and all of the side lengths are the same on here. So we can see that the regular triangle tiles the plane nicely. We've also got sort of the most traditional tile here is the square, or sometimes referred to as the regular quadrilateral. So that will tile the plane nicely. This way that I've set it up right now, and as well as the set of triangles here, that's what's called edge-to-edge tiling, where you can see that the edges match up, line up with each other. So the edge of this triangle is matching the edge of this triangle, but we could have a similar situation that would be not edge-to-edge tiling, where we would do something like that. These patterns are going to be able to continue forever and ever. That's another quality of tiling that's important, is the fact that this pattern could go on forever and ever. But we want to kind of explore today what shapes are able to tile and what combinations of shapes are able to tile. So the first question I want to ask is, this regular triangle, that tiles nicely, but what about just any triangle? So I've got here just a random triangle scalene, and I want to show you a technique here to show that this will tile as well. So I'm going to take, if I look at this side on the left here, I'm going to take another instance of that triangle and try to line it up so that that edge lines up with that other edge there, right? So I've just taken this first shape and rotated it 180 degrees, and that's over there. I'm going to do the same thing with this long side here. So this long side, I'll rotate it 180 degrees and throw it up on the side there. And then this side here, I'll do the same thing. Notice along this side here, I can rotate it 180 degrees and put that right on top there. If I just continue this pattern where I take one edge rather, and rotate the shape 180 degrees and line up those edges, I can just continue this pattern as long as I want to, right? And it'll always continue to tile. Just lining that up. And I can start to see that this is just never going to intersect with itself, right? It's always going to be right where it needs to be. And I'm not going to run out of room at any point. Okay, so hopefully that's enough to convince you that any triangle, right, whatever triangle I want, is going to tile using that technique. I can also say the same for any four-sided figure here. So let's look at this one here. This is just a random four-sided polygon. It's not regular like these ones here. But I'm going to try that same technique. If I look at this short side here, I can rotate my figure and line it up with that. Same thing with this side over here. Just line that up. And I'll do two more here just to convince you that this technique works. I can put that over here. I can put this one over here. Right. So here's my original shape, and then each of those edges has a rotated version of that shape on there. And I can just continue to line up the edges just like I did with the triangle. Line up the edges, and I get this perfect tiling pattern. So this can go on forever and ever as long as we need it to. We want to be able to say that every single four-sided polygon can tile in this way. And so one thing we might want to watch out for is something like this, right, where we've got a concave shape here. And for this one, scale it up a little bit. There may be a concern that we're going to somehow run into ourselves when we try to tile this, but I'm going to try that same technique. So duplicate it, rotate it 180 degrees. So looking at this top edge here, I can line that up like that. And for this edge here, this short edge, line it up there. For this long edge, I can line it up there, right? So I'm just taking this same shape that I duplicated and then rotated 180 degrees. And I'm applying that to all four sides. So same thing that I had over here, each edge of the original shape has a 180 degree rotated shape next to it. Now, just to show you that this pattern can continue as long as we need it to. Right, you can see that these shapes fit really nicely into the remaining spots on there. So we could say that not only do these regular triangles and these regular four-sided figures tile the plane, any triangle and any four-sided polygon will tile the plane. Another way to think of this is if we look at let's say this vertex right here, so this kind of area around here, if you think about the angles of a four-sided polygon, the interior angles always add up to 360 degrees, right? So if all of these are adding up to 360 degrees, notice how I've got this largest angle, one of the medium angles, small angle, second smallest angle. So each of these four angles, right, 1, 2, 3, and 4, are all represented in this vertex here. And we know that they all add up to 360 degrees, which is exactly what we want, right? We want all of these to form a 360 degree circle right around here. So we've successfully done that here. And we can look at, say, this vertex here. We've also got all four angles, right? This large obtuse one, 1, 2, 3, 4. All of them are coming together to form 360 degrees. Okay. The next thing I want to look at is, so we've kind of convinced ourselves that any triangle and any four-sided figure can be tiled. But we want to ask, are there any other regular tilings that work on here? So I've got a pentagon here, and if I try to tile the plane with that, let's see if I can do this efficiently. If I try to tile playing with these pentagons, I'll see that I have this gap left over. So that gap, actually, just a little peek into what we're going to be doing later. That gap, if you can picture these as being three pieces of paper that are glued together at these two edges here, they'll fold up eventually to make some 3D shapes. But for now, we're just talking about the flat two-dimensional plane, and there's no way to fit a fourth pentagon in here. For a hexagon, if you've played Settlers of Catan or another board game like that, then you already know that these hexagons tile the plane nicely. Right? So if I look at this vertex here, right, we know that the interior angles of a regular hexagon are 120 degrees. So if I look at this vertex, all right, this vertex here, and I look at the degrees of here, I've got 120 plus 120 plus 120 is giving me 360. So if we can add these up to be 360 degrees total with this regular polygons here, then we've tiled the plane, right? This one's got to be 90, 90, 90, 90, so 360. This one here, I don't have a vertex, but it would be 1, 2, 3, 4, 5, 6, 60 degrees to add up to 360. But for here, you can see that we've got the interior angle of a pentagon. So let's remind ourselves of the formula for that. So for the interior angle, the total is going to be n minus 2 times 180. That's going to be all of them added together. But if you remember from chapter 1, we can divide that by the number of sides, which is the number of angles here. So all the interior angles divided by the number of interior angles. So we've got 5 minus 2 times 180 divided by 5. That's going to be equal to 3 times 180, so 540 divided by 5. And that's going to be equal to 128. Just about. So that number there, we've got 128, 128, 128, and then this leftover piece here, right? So we can't make 360 degrees with multiples of 128. So we can use that fact to actually talk about, is it possible to have some other shapes here? So I've got like a 10-sided figure. Is it possible to have regular tilings other than triangle, square, and hexagon? And the answer is no. All right. If you look at the interior angles of, each of these regular polygons on here, there's going to be no way to line them up in order to get 360 degrees other than the triangle, quadrilateral, and hexagon. So we would say those are the only 3 regular tilings that are possible, right? And think about what that would mean if there was some larger sided figure that would work. So something more than 6 sides. We'd only be able to fit 2 of them, right? We've got 1, 2, 3 of them making up 360 degrees. This hypothetical one would have to have right? To put together, and that would have to be 180 degrees each for those sides, and that's just not going to work out for us. So, yeah, triangle, square, hexagon, those are the only three regular tilings, right? It might be possible for us to manipulate these into, shapes that aren't regular. Five-sided ones, there's plenty of five-sided shapes that will tile. We'll look at those a little later, but for regular, just these three. So those would be considered regular tilings. There's also this idea of a semi-regular tiling. So a semi-regular tiling is a tiling that uses regular polygons, like I've got here. So these are all regular polygons, but it uses more than one type. So one semi-regular tiling, so again, that's a tiling that uses more than one regular polygon on here, would be this one here. So this one's made up of two squares and three triangles. So that shape there, that's going to have that's what we call a semi-regular tiling. So we've got 60 plus 60 plus 60 plus 90 plus 90. That's making up our 360 degrees in here. Right? So there's a list of semi-regular tilings in your textbook, but if you want to figure out if something works, you just need to look at the interior angles and see if they add up to 360 degrees. I do want to warn you, so just adding up to 360 degrees is not always going to produce a semi-regular tiling. So I've got here, for example, a decagon. So this is a 10-sided figure. And I've got two pentagons. So these shapes, it would seem at first glance anyways that these three shapes form a semi-regular tiling. Because I can, really truly fit, and the angles do work out, right? The angles truly do add up to 360 degrees here, right? The problem is, for a semi-regular tiling to work, each vertex needs to be the same, right? So each vertex needs to be completely identical. So what I mean by that is if I look at this vertex here, I've got one dodecagon, and then I've got another pentagon and another pentagon. So each vertex should have two pentagons and one decagon. So this vertex works out fine. I'm going to keep trying to make these. Okay, so you can see I've got, this is fine so far. I've got this dodecagon, and this vertex also has one dodecagon, or sorry, not a dodecagon, that's a 12-sided. This decagon, 10-sided, two pentagons on here. That's working out just fine, right? So no problems so far. But this vertex here, right, if I think about this setup here, this would need one pentagon, two pentagons, and a decagon in there. And if I try to fit it in there, you can see I've got this overlap here. So the fact that I've got this overlap here means that even though I've added up to 360 degrees, this is not a semi-regular tiling. If I try the same setup over here, where I try to extend that tiling on there, I'll show you what that looks like when you try to extend this pattern. So this particular arrangement, triangle, 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 and then two squares, this one can be repeated as long as we need to, all right? We'll never run out of space. So I'll just show you, all right, this pattern can be repeated. So that pattern can continue as long as we need it to, and we're not going to run out of room. And if we look at each vertex, we can see that we've got 3 triangles and 2 squares. That's true at every vertex. So this would be an example of a semi-regular tiling. A semi-regular tiling, again, it's got to use 2 or more regular polygons, and each vertex needs to be the same. So meaning each vertex has to have the same number of shapes. Okay. One way that we can talk about these semi-regular tilings is, and even any tiling, is using something called the Schlafly symbol. Okay, so that's spelled like this. So the Schlafly symbol is a way to talk about what tiling we're looking at. So for this one here, looking at this vertex here, I have a regular four-gon or a square, a regular quadrilateral, a regular quadrilateral, triangle, triangle, triangle. So this is a four-sided, this is a four-sided, three-sided, three-sided, three-sided. So the Schlafly symbol for this tiling be, I'm just going to move clockwise around here. 4, 4, 3, 3, 3. Right? Meaning that I've got a four-sided, four-sided, and then three-sided, three-sided, three-sided. This is one way to write the Schlafly symbol. So sometimes this comes in a brackets like this. Another way to write this, the starting point is not super important. I could call this here the starting point and say this is 3, 3, 4, 4, 3. Right. So these are the same Schlafly symbol, or they describe the same tiling on here. So you may be asked to, at some point, interchange between 2 different Schlafly symbols, but you can think about this as being like, you're kind of in a row, right? Like you have these numbers in order, but you can always take the first one and put it back here, right? And you can continue that process, and you can always take the first one and put it here in the last component here to get that 4, 4, 3, 3, 3. Okay, so that's the Schlafly symbol. You'll see it talking about, so again, Schlafly symbols are for regular and semi-regular tilings. this a complete okay, so that vertex there, we can see this has 1, 2, 3, 4, 5, 6 regular triangles. So the Schlafly symbol for that would be 3, 3, 3, 3, 3, 3. So 1, 2, 3, 4, 5, 6 triangles. You may also see this as 3 to the 6th power. Here, 4, 4, 4, 4, or Schlafly symbol of 4 to the 4th. Okay. Going back to the semi-regular tiling that we were looking at. So here's a example of some semi-regular tiling. If I look at this vertex here, I can actually make, rather than just making a circle around that vertex there, I can create a polygon that goes through the center of each of these shapes that I've got here. So a little bit more accurate about this. Okay, so trying to find as close to the center of each of these shapes as possible. And what I've made here is a polygon, right? Pentagon, in fact, in this case. So this is not a regular pentagon, right? There's a little, offset for each of these. But this pentagon is actually what's called the dual polygon. So if I look at, if I try to make another polygon of that type around this other vertex, here you can see I've made another pentagon, and if I try that same thing, try that same thing over here. I also make a pentagon. And it turns out that that pentagon, so this pentagon that I'm making is called the dual polygon. Right? That dual polygon there actually also tiles the plane. So this is not a regular pentagon, like I said. This is just a pentagon that is going through the center of each of these shapes here. But that pentagon also tiles the plane. Each pentagon is made up of a certain number of, a certain fraction of each of those shapes. So if I look at, let's just look specifically at this one over here. So this dual polygon, this pentagon right here, if you look at the contents of that, it doesn't have a full square, but you can see that it's got 1/4 of a square. So that dual polygon has 1/4 of a square, and it's got another 1/4 of a square. It's also got 1, 2, 3. So each of these, if you can kind of picture this being broken up, this is into 3 pieces. This is a third of a triangle. rather than say a third of a triangle plus a third of a triangle plus a third of a triangle, I'm going to say this is a third of a triangle times 3. So this dual polygon overall contains 1/4 of a square plus 1/4 of a square plus 3 1/3 of a triangle. This is the same as saying it's got 1/2 of a square, and 1/3 times 3 is 1 whole triangle. Now, this combination here, this is sort of the contents of the dual polygon. If we don't want to talk about things in terms of fractions, we can talk about something called the module. So the module removes the fraction. So in this case, what we would do to remove that fraction would just be to multiply everything by 2. So if we multiply everything by 2, we get 1 square and 2 triangles. Right, so that's multiplying everything by 2. The reason we give a specific name to this module is it's made up of, right, whole shapes here. And one way to think about this dual polygon is in terms of these pentagons, right? These pentagons make up a dual tiling, right? A second way to tile it. But if I grab 1 square and 2 triangles, like this module is suggesting, here's one version of that. This module here also tiles the plane, right? So kind of, if I take this collection of shapes here, this module, and I just copy and paste that same thing, I can make a semi-regular tiling with that, right? So that module consisted of 1 square and 2 triangles. That's not the only way that I could have made this 1 square and 2 triangles. So go ahead. Right. This is another version of the same thing, but I can take this and tile the plane just as easily with this shape. I may need to rotate it in order to get that same semi-regular tiling. But yeah, if I've got 2 triangles and if I've got 2 triangles and 1 square, then I can tile the plane with that to my heart's content. Right, just to show you, it may not seem like I can do that, but right, the pattern continues on as long as I want it to. All right, that is all the vocabulary that you'll need in order to solve these problems. So we've got the Schlafly symbol, we've got the dual polygon making up the dual tiling. We have the module, which is getting rid of the fraction to come up with a collection of shapes. And then we've also got the regular and semi-regular tiling. So we're going to use that in the next video to solve some quiz problems, and I'll see you there.